Let's continue the afternoon session. Second speaker is Lukas Woike, and he will tell us about spaces of conformal blocks, correlators, and factorization homology.
Thanks a lot for the invitation, and thanks to the organizers for organizing such a nice event place. So yeah, I will speak mostly about this preprint, but I will also mention or implicitly use works with Adrien Brochier, Lukas Müller, Christoph Schweigert, and Yang. And I will start with a reminder on modular functors. So this is going to be short because we have seen these things multiple times. So a modular functor is a consistent system of mapping class group representations. And what it does is that it assigns two compact-oriented surfaces with labeled boundary components vector spaces that some people might refer as one representations of mapping class groups or spaces of conformal blocks, depending on the origin. And I would denote it like this. Yeah, F for functor A is the label set, which then by evaluation on the cylinder immediately becomes a category. In fact, this category of labels is, and this is something that I showed with Lukas Müller, this is always a cyclic framed E2 category, so it's balanced graded, and it has also a non-degenerate symmetric pairing on it. And this vector space that is being assigned to the surface, this comes with the mapping class group representations. This might be projective, so there might be extensions of the mapping class group involved too, to the extent that you like, so you can decide on what kind of extensions you might allow. Today, we will concentrate on what is one might refer to as finite rigid logarithmic CFT. So this category of labels is not necessarily a modular fusion category, but I will assume that A is finite and rigid. Yeah, it's a monoidal category, so I can ask that. And I will also ask FA to be compatible with orientation reversal. Under this assumption, you can prove that then A is actually a not necessarily semi-simple modular category, and that the modular functor is the one that is constructed by Lukashenko. You might also, and some people do that, you might also just start here and say that finite rigid logarithmic CFT is simply that. So there's a paper by Fuchs and Schweigert where this is one of the axioms. But you can also ask this, which is a little more basic, and then you can show that this holds. But this is just maybe a psychological thing.
What does it mean that FA is compatible with orientation reverse?
It is a slightly more sophisticated version of the fact that the orientation reversed surface is going to be sent to the contragradient representation. You cannot literally ask it, you have to be a little bit careful, but it's essentially that. You come up with the involution on the cyclic frame E2 algebras that is composed of dualization and the orientation reversal, and you're asking this to be a homotopy fixed point with respect to this homotopy involution. Okay. So, and another conventional thing, so I will ask these modular functors to be left exact in the boundary labels. This is a matter of pace, but this is the thing that Lukashenko did, and I will also do that. Okay. So then the second thing is something that was also mentioned, and those are correlators. So, a consistent system of correlators for the CFT with monodromy data A, and yeah, since today we look at this case, A is a not necessarily semi-simple modular category. Has an underlying object. B. And B is in A bar A. A bar is A with the, but you reverse, you invert the braiding, the balancing. This is what you would, so this is the supposed to be the bulk field later on. And we're asking this to be self-dual. This means that there is an isomorphism between B and B dual, such that, so what does it mean to be self-dual? This doesn't, so it means the following. So I have this commuting triangle where here I have the dual of this identification of the object and its dual. Yes, here it is. And here I dualize this identification. This is supposed to be the Same as I already had under the pivotal structure that I have. And then with vectors, that live in the spaces of conformal blocks. For this modular functor, yeah, it's not the original one, but it's the one that I get after combining left and right mover. So this is always implicit. And the boundary label that I fill in is always this object. And yeah, this is essentially the thing that Aaron already told us. So it's going to continue. Small remark here. So this thing here, the mapping class group representation, is actually non-projective. This is very important. This is, I think, in the semi-simple case, this was known. The first proof that I'm aware of in the non-semi-simple cases in the paper with Lukas, Christoph, and Young, where we showed this using the string net model, where it's somehow apparent that this is actually a non-projective action. And these vectors, so they are invariant under the mapping class group action and gluing. And on the cylinder, this is what I get back is the self-duality pairing. So on the cylinder, this gives me a non-degenerate pairing on this thing that comes from this thing. So whether I have an identification of B with its dual or a non-degenerate symmetric pairing on B, that's the same thing. On the cylinder, I want to recover this. So this is a unitality condition.
Make a trivial comment. So this is a consistent system of bulk field correlators.
Yes. So yes. So for the that is correct. The reason why I didn't write it was that I was not yet done, because we will ask here that these correlators are actually open-closed, because this thing happens to be an open-closed modular functor, and I want this to be compatible. So we're asking a little more, but you're correct. So far, this is a bulk field correlator, system of bulk field correlators. So since this thing is open-closed, we want more. This is something I will only sketch. I will not spell this out in the same detail, but what we have here is that we can also evaluate this modular functor on surfaces where we might have some boundary components that are parameterized like these ones that are labeled. And then I want to put here on those that are parameterized B, but there could also be ones that I'm even going to leave empty. This one here is not parameterized. I'm not going to label this. And then there is some of the new feature that we don't have for the pure bulk field correlators, and this would be embedded intervals to which we associate another object that I call F. And there could be, I mean, you can put these intervals where you want. You can put 1, you can put here 2 on this boundary circle, maybe you put none. It's fine.
So what kind of output is that?
Sorry?
What kind of output is that? Is that a functor from some?
Right. I mean, this here I've plugged something in. So this is just a vector space, and then also inside these vector spaces, I would want again mapping class group invariants that are compatible with gluing. So I would just write here plus gluing constraints. And there's gluing not only along the boundary circuits, but also gluing along these boundary intervals.
So I don't think of the unlabeled circle as kind of having the entire category sitting over it.
No, no. You should think of it as a puncture because an unparameterized boundary component would also be a puncture.
And you didn't say what F is.
I did not say this. So the F. Okay, that's a good point. So the F is in one copy of A, while B, so I will just write it here for as a reminder, is in these 2 copies. Yeah. Okay. And so the main problem or the main step in resolving this or in exhibiting such vectors, because this is what we want to do now. This is the open part. But before, let me mention that. So in the semi-simple case, there is a solution via the FRS theorem. And since we have heard so much about this, I will not explain this further, but in the semi-simple case, so for modular fusion categories, there is a solution for all of this using the Rechtstückchen-Reif construction of the modular fusion category A. And so beyond that, the thing that is a very reasonable starting point is to look at the open sector, the open part of this problem. And if I just look at the solution just for the open part, I will refer to this as this consistent system of open correlators, or simply open correlators for brevity.
So open is the unlabeled part?
The open is the thing for the F where I have no parameterized circuits. Yeah, so this would then also be unparameterized or with additional embedded boundary intervals, but I only have parameterized boundary intervals. Yeah, so there's just the F.
Is your B associated to the 2 circles simultaneously or just 1 circle?
It is associated to 1 circle.
1 circle.
So in this open part, this now means that we are looking for an open correlator or a system of those for the open CFT with monodromy data A. So what does this open CFT do? And so the only thing that I need to explain for this is what this does on disks that have, so what color did I have that? That was yellow. So but one of the easiest operations in the open surface operator, surfaces with parameterized boundary intervals, is this one. This is a disk. And then I could have a bunch of boundary intervals. And so for this, I need a left exact functor that I associate to this. And if, well, I have this category A, and this is going to send this to the functor that homes from the unit and then takes the boundary labels that are here. So here I'm keeping those variables, so that it's going to be a functor in these labels. I'm not putting any letters in, but here I have 1, 2, 3, 4, 5. So here I wrote 3. So let me instead write dots. Yeah, you put them in cyclic ordering. This is in particular a pivotal category, and this is why this makes sense. Yeah. So in a slightly more fancy language, what you're using here is that so that your modular category is in particular a pivotal finite tensor category. This is a particular instance of a cyclic associative algebra. And this is why you get these vector spaces. And this actually extends to the entire open surface operator. And even more is true, this data is really equivalent to this extension. Yeah, it's in one-to-one correspondence. So this is the first very important observation. And this is a result with the other Lukas. So there is a contractible choice. One open modular function. I will quickly write what that is. So this means that I want to provide for all surfaces, for all operations in the open surface operator, meaning that I have compact oriented surfaces like this, and then I have a bunch of embedded intervals. Maybe here I have 1, maybe here I have none, maybe here I have 2. That makes in total 3. Or let's say I would denote this number by n, so that let's say this is n many. This is of course just an example that I drew. And there is then for such a thing a left exact functor. And this is compatible with the gluing along intervals. And I denote this extension by a shrink. Yeah, no connection to causal duality, but there's only a finite supply of symbols, so we're just using it. So this is for all the surfaces, and this is compatible with the gluing along intervals. No gluing along boundary surface. This is not included. So this is something that is actually not. This is rather difficult, at least in principle. The good thing is that there are things that you can use to prove this. The main thing that is hidden in this statement is the ribbon graph description of surfaces. So the statement is essentially that if you take this cyclic associative operator, you can freely complete it to a modular one, and this is the open surface operator. This is a concept that was invented by Kevin Costello, and then this statement that I gave you, that somehow by completing this that you actually get the open surface operator. This is essentially, up to some details that we had to add, a result of Jeffrey Giansiracusa. Yeah, and this is an extremely
So you could write down the names.
yes. So this is using results of Costello and Giansiracusa, but they are using also the ribbon graph description of surfaces. There's This is then also work of Koncevich and many others. This is a very long list of people who have figured this out. But yeah, so there's this extension that you can do from these kind of things to the surfaces. And what you essentially do is that you take this and then you glue these intervals together. And every time you do that on the algebraic side, you will do a coend. So it's not even that surprising. And so it's a very explicit construction at the end of the day. And now you can solve the problem of correlators for this thing, just the open thing. So you can ask, what is the open correlator? So this is a word that I'm using. I'm not so sure whether open correlators are really a thing. This is, for me, this is an auxiliary object. Yeah, but this just means that I'm trying to solve this problem just for the open part.
Do I understand that I can't make the whole circle yellow?
Sorry?
Do I understand that I can't make the whole circle?
You cannot. No. This is not possible. So a correlator, oops, or rather a system of correlators for brevity, I would write it like this, for the open modular functor A is exactly a symmetric Frobenius algebra in A. And this is something that I proved with the modular microcausal principle. What this essentially does is that it uses this classification of open modular functors through their part that is just given by the disks twice. Yeah. So if you want to, for instance, if you want to know what associative algebras in a categorical associative algebras are, then you have to first figure out what are associative algebras in categories, so some monoidal categories. If you have a monoidal category, you can define an associative algebra inside. And this is exactly that, but it does this for the modular open surface operand. And this reduces this with these works of Costello and Gian Siracusa to figuring out what cyclic associative algebras inside is a categorical cyclic associative algebras are. This pivotal finite tensor category is such a cyclic associative algebra. Not all are of this form, but this is a particular instance. And then you look at symmetric Frobenius algebras inside.
So I'm a little confused about the relationship between the FA. So I start with FA, and I go to this other place, and I draw the same picture. And now it's A shriek. So
I did not explain the relation. Yeah, this is I did not explain the relation between this guy and this guy. This is
different things.
Those are different things. They're not. I will relate them. And this is. I will do this now. I will do this now. So,
sorry, one more thing.
Yeah.
So you say a correlator for it's exactly the symmetric reduce.
It's in one-to-one correspondence, or you can also turn them into both into group points. Yeah.
Okay, it's just a bijection. So
it's an equivalence. Yeah, it's exactly. Yes, exactly that.
You don't need any extra assumptions on the Frobenius algebra,
No.
right? Nothing like
No,
exactness.
because this is just the open part, and in particular, there's no gluing along boundary circles. This is why so far there's no mention of specials. So let F be a symmetric Frobenius algebra in A. So this gives us, well, something that you might want to call maybe correlator candidates. Yeah, so vectors of the following form. It gives you inside.
So you had this object F before, which defined the open extension, and then symmetric Frobenius algebra in A, is it related somehow to this F?
So first of all, so one thing is a little bit unfortunate, and this is my inability to correctly write these calligraphic letters. So this F of index A for the modular function.
Not that F.
Okay, I was worried.
F to the right on that. Yeah.
This F.
Yes, this.
Yes, this is yeah. This is now going to have to become a symmetric Frobenius algebra. This is because if you restrict all these requirements for the correlators just to the open part, then you can apply this, and then you know that the F has to be the F has a symmetric Frobenius algebra.
Just to write in the theory of symmetric Frobenius F in A.
Yes. So this we can call it F, and then this would not be misleading because this F would then be this F. Yes. Okay. If you now take this open modular functor, you put in a surface, you put an F everywhere for every interval, then you get from your symmetric Frobenius algebra, you get vectors inside. This is the open correlator. So now this is something that we have. And now comes the reply to Chris' question. This thing is related, this space here for the from the open modular functor is equivalent to the modular functor, the Lukashenko type modular functor for the Drinfeld center of A. But now I cannot put F here because F is an A and this has to be the Drinfeld center. So I need to put F for this to make sense into the Drinfeld center, and I do this by applying the left adjoint to the forgetful functor. So, this not delta. This is here. There is the forgetful functor, and then there is L. This is the left adjoint. It's also the right adjoint because it's a modular category. This isomorphism here is of course not supposed to be obvious. This is something that I showed also with Lukas Woike. And the Drinfeld center here, you can replace this with 2 copies of A. Yes. And then, okay. And if I do that, then this object, LF, if I don't write it in the Drinfeld center, but instead I write it in the equivalent category A bar A, it's also a well-known object. This is going to become a coed, namely this one. And I will give this the name BF, and I will put a 0 here. Yeah, so I call it LF in the center. In this one, it's this coend or end again. Modular categories, in particular unimodular. Okay. So now,
Sorry,
yes.
you don't have to reply to this now if you don't want to. But how is rigidity needed in your theorems? If you want to reply to this later at the end, please.
So far, I mean, okay, maybe, okay, so for these things here, Drinfeld center, this is something that I don't want to touch if it's not rigid, this also, but let's forget about this. Then this thing here does not need rigidity. In general, an open modular functor is something that you would get from a pivotal Grothendieck-Verdier category, and with a symmetric Frobenius algebra, in the sense of your paper, where of course you have to be careful with where does the pairing land and so on, this is still true. And this part, the open part, is still true. Yes.
And for your open part, it would be still fine if the dualizing object is not isomorphic to the monoidal unit.
Doesn't have to be isomorphic to the monoidal unit. Then this thing here that I wrote would not be correct. Then you put here the dualizing object and it's fine. Yeah. Okay, now, so what we have are now these vectors inside the space of conformal blocks for the twin-feld center, or equivalently 2 copies of A. And now, and we also have vectors inside that are invariant under the mapping class group. And they are, because they are open operators, so to the extent that the mapping classes already act, they are invariant, and they also glue along intervals. And now we have to upgrade this a bit. And for this, we will use factorization homology. So factorization homology, this, so I cannot really define this here. This is a concept that is, at least in the form that I'm using this is something that you can find in the work of Lurie. I'm not so sure to what extent a global reference to the work of Lurie is helpful, but I will still write it. And so this is inspired by the concept of chiral algebras by Beilenson and Twinfeld. Very roughly, what this does is that you take A, and A is a framed E2 algebra. In particular, our modular category would qualify here, but could be something much more interesting. And also, I'm writing framed E2. I'm just directly going to the 2-dimensional case. Factorization homology, you can do this in every dimension, but I'm doing it here for the 2-dimensional case. And then you integrate this over a compact oriented surface. And the result of this is again, so okay, this is a, let's say, framed E2 category. So this is a balanced graded category. The result of integrating this over sigma using factorization homology is again a category. And what this does very roughly is that you take all embeddings of a bunch of disks, and a bunch of disks can also mean no disk. But you embed all of these, and for every disk of the embedding, you add a copy of A. Such a direct sum, of course, is not a very intelligent object, but then you simplify it by imposing relations whenever 2 disk embeddings are already contained in a bigger disk. And you do this in a homotopy coherent way, and this gives you factorization homology. The good thing is that with this sort of definition, I mean, it's not a free definition, you will never calculate it with this definition. You will use other techniques. And so what is the connection to the things that we have seen? And the connection is that this open modular functor has, it has a description in terms of factorization homology. So if you have a surface going against such a surface, and it has the datum of a bunch of parametrized intervals.
I'm so confused.
Then for every such interval, the category, so for every such interval, this category will act on factorization homology. And since we have frequently seen already in this conference the notion of a module category, I can also use this. So AN, monoidal, in particular, monoidal category AN acts on this. So this is a module category over AN.
I think it's a little bit confused. So you really, all your pictures, you don't have an outgoing boundary.
No, yeah, I should have, this is something, this is a remark that I should have made in the beginning. So something that I'm not showing, I'm showing here, but so we're doing this in the language of modular operands, in terms of Getzler and Kapranov. So there is no ingoing or outgoing. There's just one thing, and they're both ingoing or outgoing as you wish. This is why there's always a non-degenerate symmetric pairing on this A. This is the thing that gives you the duality. This can be a weak duality, a Golden-Verdier duality. And this is the thing that you use to turn ingoing into outgoing if you really want this, but you don't need it. You can also just have one thing. It becomes much easier.
There's still some composition operations in.
Yeah, but then the composition is by inserting no, this comes from the pairing. So instead of composing it, you will contract two such things with the pairing, and then this amounts to the composition. Yes. Yeah, it's the same thing. It is just technically a lot easier. For TFTs, ingoing and outgoing is quite important. If you just have the modular functors, then I think it makes things more complicated in a rather artificial.
Well, I disagree about this artificial, because what you're assuming is pivotality. So it's the existence of dualities. And it means that in a sense, your objects in the CFT are all small. They don't have a certain finiteness condition.
They have to be. They have to be.
They don't have to have rigid duals. They can have GV duals.
Yeah, they have to be with respect to this weak duality. They have to be self. Yeah, this is why for the correlator, one piece of data was this safe duality. Yeah, but once we have that, then we can somehow just have one thing. So I always draw them to the left, but it's yeah. And there's another remark that I want to make. So there is inside factorization homology, there's a canonical object, because factorization homology is functorial with respect to embeddings. And so if you embed the empty set into your surface, which you can always do, you get an object inside, because it's a functor from vect to this, and this amounts to an object. And this is an object that so this appears in work of Bensley, Rochier, and Jordan. And of course, I don't cite them because they said that there is this object. This is not worth mentioning. The main point is that this is an object that knows a lot about this category. This is under a certain hypothesis. This is going to be a generator that allows you to reconstruct the category. This is why this appears in their work, and it also appears here. The connection is that so for any finite ribbon category, so A was basically modular all the time, but since this is maybe also important for other reasons, I will write it in slightly more generality. If I take a surface and I evaluate this open modular functor on the surface, and I put in a bunch of objects at all of the n many parametrized boundary intervals, then this is canonically isomorphic in a mapping class group equivariant way to the Hom space in factorization homology from O sigma, and then I write O sigma again, and now we have to put in somewhere these objects, but I told you that it's a module category over AN, so we can take all of these and have them act on this O. So this symbol here, this is for the action. And I said mapping class group equivariantly, but the best statement to make is that, well, this is an open modular functor. You show that this is also an open modular functor, and those are equivalent as open modular functors. So this is what I'm going to write here, as open modular functors.
sorry, so is my category an input to my open modular functor, or is it an output from my open modular functor? So the open modular functor has something to do with the script A. And the script A comes out of the modular functor, or I have
so you take this thing and you build the modular functor from it. Yeah. So this you have your A, and then on disks with marked intervals, you use these hom spaces to define it. And then we had this statement here that told you that there is now one extension to all surfaces.
Sure, but the question is, do I need A as an input before
I need A as an input? This is somehow the thing that you want to use to describe the CFT, the representations of the BOA for
open functor relative to a choice of A.
Yes, this is I mean it's literally equivalent. You can take also an open modular functor, you restrict it to disks, and then you will get back something that in general is only a pivotal Grothendieck-Verdier category, and that here in particular was actually a modular category, which is ribbon, and then if it's ribbon, I can see it as pivot. So this is something that does not see the.
So when it is semi-simple, is it possible to say what is the factorization homology and the object? Just to make a trivial example.
I can tell you, but it's a big disappointment. So if A is a modular category, and this is it can even be non-semi-simple modular category, and sigma is closed, then the factorization homology is vect. This corresponds in a sense to this 4D TQFT that Francesco was talking about being invertible.
So what is the object in the vector then? What is the vector space?
So the point is that the identification with vect is very non-trivial. The category is in a sense trivial, but it's trivialized in a very non-trivial way. This is identified with the category of vector spaces, and
what is
so it corresponds to a vector space, and this vector space is the vector space FA of sigma. It is the space of conformal blocks. Under this identification, it corresponds to the space of conformal blocks. The pointing is so you have, if sigma is closed, this thing here, so let's forget about the boundary components. This is in particular a vector space, and what I'm telling you is if you trivialize this category, this is the non-trivial part, you have to trivialize in a very specific way. You identify it with vect, then O is going to be same.
There are not many ways. Because the equivalences of vector.
Yes, okay. There are not so many ways. It's unique up to non-invertible scalar multiple. So you're correct, but it is somehow the identification is so the identification is the skein module. I will explain this later, but it's somehow it's the skein action that identifies this with this thing. Yeah. So what did I want to? All right, and so this implies, as a corollary, that this thing that we had this vector space where we had sigma and we had plugged in this object that we constructed here, that this is isomorphic to the homs in factorization homology. And here you put in always F. So the reason why this is important is that somehow this is what this thing here is what replaces in this approach the holographic principle in FRS, and it's very different because it uses factorization homology. It doesn't use the TQFT, but it replaces that because it describes this two-dimensional quantity through a three-dimensional one, because it describes this as morphisms in factorization homology. Factorization homology is two-dimensional, but the morphisms are three-dimensional. They're skeins in surface times interval. So this is a three-dimensional thing, or it's the two and three-dimensional part of this generalized non-semi-simple skein cranietta TQFT that Francesco was talking about. And so it says also this, so this thing here has, again, this higher dimensional origin. And this is not only something that is nice to observe, but this is something that that one actually uses to continue the construction. I should mention that somehow when I say that this identifies this with this skein, or that somehow that there's a connection to the skein TQFT of that Francesco was talking about, that this uses a lot of identifications of all these factorization homology things with this skein picture in a non-semi-simple setting. And this is work of Jenny with Benjamin Hayun. I think that you will talk about this next week. And then also of Lukas Müller and myself. So there's a lot of steps, because it's not, there are a few steps. And okay, so now the thing that is missing from this are two things. So there are two things that the construction, as I have explained it so far, does not do. And the most important one is gluing along boundary circles. And so I will shorten this here a little bit for time, and so I will just tell you what needs to be done. So the main information is that for the compatibility with the gluing along boundary circuits, F needs to be special. Yeah, so if we want to take these vectors that I already gave you, and if you are also asking for the compatibility with the gluing along boundary circles, you want this to be special. And now if you have this, then you might think that this is almost everything is fine, but there's one small detail that is still a little bit annoying. So these vectors, they are compatible with the gluing along intervals, with the gluing along boundary circles. They are mapping class group invariant, but there's one problem. If you take a cylinder and glue it to a cylinder, then you can see this, then you get again the thing for the cylinder. But the cylinder is not going to be sent necessarily to the pairing for this object here. Or in other words, if I see it as an endomorphism of this object, this is not going to be the identity, but this is going to be an idempotent. This is a well-known problem that shows up in exactly the same way in the other construction. So what you need to do in order to fix this last remaining point is that you go to the image of this idempotent. So this is something that I will just note here, because there's no, with regards to this point, there is, this is, for instance, in the stringnet version of for the rational correlators in the book of Fuchs, Schweigart and Young, they explain this, and that there's no, this works in the exact same way.
So now with special, you are outside quotient equity, you need rigid.
Yeah, this is everything that I'm saying is finite rigid. The Groten-Dick-Verdier thing, this was just in response to your question for the open part. Okay. No, I'm not. No, I don't want to say what replacement you would have beyond
You're
that.
saying I choose some idempotent, then I split F up according to the idempotent, I basically conjugate by the idempotent, then I have a new algebra. Is this what you're talking about? This idempotent?
No, what I'm saying is that the cylinder. So the cylinder, I can see this as an endomorph. It gives me an endomorphism of this object. And for the unitality, because of the unitality condition for the correlators, I would like this to be the identity. But it's not, but it's going to be compatible with gluing. This means that it's going to be an idempotent. So, and if you have an idempotent and you want this to be, if you want an idempotent to be the identity, you can get this by going to the image of the idempotent. You go to the image of the projector, and then it's fine. So I could just, and then pass to image of the idempotent. And this is going to turn somehow this raw version of the bike object to the actual version of the bike object. I will denote it by BF.
So it's the same thing as the algebra that I get by putting E on both sides of the algebra. I have some idempotent, and so it's called idempotent E. It's some element, right? And then I could take an algebra. I put E on one side, E on the other side. I get a new algebra that cuts up the old one.
Yes, I think this is one way to.
It's the same.
Yeah, I mean there are many descriptions. You can there's an equalizer description, there's a co-equalizer description of it, and so.
In your proposition, is special necessary, sufficient?
Here it is, it's necessary and sufficient. I have to mention here that so the thing that I am doing is somehow more it's in this picture, in the classical picture of, for instance, this article of Everest together with Fiesta for this uniqueness, open closing with no mention of module categories, one thing for the interval, one thing for the bulk. This is the thing that I'm looking at. I'm not making statements about things that are not in that situation.
But can you say a bit more where the special comes from? Is this to get this gluing working?
Yes. So gluing along circuits is almost gluing along intervals. If you glue along intervals and actually want it, I mean, it is identical to gluing along circuits, but if you glue along intervals, it creates a puncture, and then you need to somehow evaluate on this puncture. And the thing is that the Frobenius algebra, it can wind around this puncture, it creates a bubble, and if you cannot get rid of this, then you get a problem. This is
so we are just we reached the following question. Is it true that B0 is not necessarily commutative, but BF is commutative?
As an algebra in the center.
BF is a braided commutative algebra.
And B0 is not.
F. B0 is not.
And BF in some sense is just a commutative center.
Yes, that is true.
Left
that is true. This is going to be, I will say this at the very end if I have time. This is so I mean this is going to be if you want. So this is the appropriate version of center for every version of center that you can come up with.
It's called the full center in FFRS.
Yes, I will say this at the end, how this is exactly related. So this is a consistent system of correlators, and all such systems are of this form if one asks for a compatibility of the open and closed part. So I'm afraid that I will not have time to spell this out, but this is essentially it's essentially the compatibilities that feature in FRS plus PSAT, the open closed paper. Because if you have already the open thing, then you get candidates for the closed thing by putting an interval on the circle, and you want the extension to the closed part, you want this to be that, yeah? So essentially you're saying, I already have my given F. I don't want an independent B. B is supposed to be the center, and this is the only reasonable thing to ask, because on the interval we put A, on the circle we put the center, and this relation between F and BF just internalizes this connection. Yeah, it's the microcosmic version of this connection, so this is the thing to ask. So I hope that, okay, I still have time to say something.
Start with this last point. Do I need to ask for compatibility with open closed part?
No, you don't. No, you don't need to ask that. I'm saying that I'm saying that you should, and that if you do all of these forms, I'm saying, I mean, you can differ on.
Well, I guess the question is, like, you know, if I think about just CFT in some abstract sense, would I expect for this to occur, or is this some kind of imposition?
I mean, this is essentially the compatibility from that is also imposed in the rational case, and I don't want to mess with that, so I just take the same. So I want to say one thing about the torus partition function. And the torus partition function that we built from a special symmetric Frobenius algebra, this is something that I would note by ZF. And this is it's the correlator for the torus, but the non-trivial point about this is that you can also see it as an endomorphism of the space of conformal blocks for the torus. This is something that in the non-semi-simple situation is a lot more non-trivial, because you don't have the TFT in the background, but I think you want this picture because you want to talk about coefficients of this endomorphism, and this is something that you can do. And so one can calculate coefficients and one does this at, I mean, okay, there's a in the paper I define these coefficients. This is something that is a priori, this is not defined, and you have to think about what how to do this, but it depends on two projective objects. So there are coefficients at projective objects, and those are essentially the coefficients, and I'm evaluating at the vectors at the vectors inside the torus conformal block that are given by taking this projective object, and then you put the identity of this object in here. This is the projective object. So this is the admissible skein. This is actually a vector inside the space of conformal blocks for the torus, and then you can apply this thing. And something that I will just explain in words for time constraints is that, maybe I write it schematically. So if you take this vector for a projective object Q, and you take this torus partition function, so this is an endomorphism, so I can apply this, and then I take, as in the first FRS paper, I take then this other object that now is also projective, and I put this one in disk times S1. I take the union over the two torus with disk 2 times S1 but opposite orientation. And here I put this other object. I also take the dual. This is a conventional thing. Then this thing is an element in the admissible skein module for S2 times S1S in FRS. There also you get this partition function by closing up, or by having something on the 2 sphere, by closing it up, by taking a loop. And this is now in the admissible skein module. And this is canonically K. This is something that we heard in Francesco's talk. Yeah, it's not only K, because he told us that it's an invertible field theory. This is canonically K. This is a number. So this tells us, and this is this number so this is a number, and this is what I define to be this coefficient. You have to be careful. These things are not a basis for this vector space. I'm still extracting coefficients. I'm not saying that this is a basis. But so the reason why those make sort of sense is that you can show that these are non-negative integers, as in the FRS paper in the rational case. There's a non-negative integers, and if you take for F the unit, so if you do the Cardi case, then these numbers that you get, they are this gives you the Cartan matrix, and this is so this is something that at least in hindsight justifies this a little, because this is somehow in line with a proposal, I should say proposal / theorem of Fuchs is that and Schweiger to have considered the Cardi case in the Hopf algebraic Cardi case, and who also thought about what these coefficients could be, and their conclusion is the thing that makes sense, and there's a lot of justification for this, is that those coefficients, they should be the entries of the Cartan matrix, and they call this the Cardi-Cartan modular invariant. And this definition, yeah, by somehow imitating the rational FRS strategy for calculating this coefficient by having the partition function as an operator act on this object, and then by taking the union of 2 genus 1 Handel bodies, the one with opposite orientation, thereby getting a link in S2 times S1. This is canonically K. You get a number, and this is. But now this is all in the framework of these, admissible skeins, etc. As maybe as it should be, and it's still a non-negative integer, and it gives you the Cartan matrix if your Frobenius algebra is the unit, which of course is the the easiest case. And yeah, I was happy.
Any questions?
So the first formulation for arbitrary F, do you know what this is a dimension of?
Yes. Like this
For arbitrary F, yes.
Yes. So so you have already asked what is the dimension of, because if it's an integer, then it has to be a dimension of something.
No,
and
because it is a dimension.
Yes, it's so. So this is really this part once you concretely calculate, which of course here in this setting is a bit more difficult because of all this factorization homology. But once you do it, it is not so different from the rational case. So you have the object P, F, you do a total parity 4 operation. Here's the Q. So this is the FRS picture that we know, right? And so this is a diagram that of course still makes sense. And so how does this give you the number? Because that part is a little more tricky. And what you do is that, so all of these are anchored on a sphere. And also this entire thing, this object here, PFQ, this is projective. Yeah, so this is really an admissible scaling because these objects are projective. F in general is never going to be projective, but the total thing is projective. So this is as an FRS. And now, since this is sphere times interval, this is a morphism in the factorization homology of the sphere. And factorization homology of the sphere, by what I said earlier, you can identify it with vect. And since you can identify it with vect, you can take of such a morphism, you can take the trace. As you said, I mean, there could be multiple identifications with vect, but the traces will not depend on the identification. And so there's a well-defined trace. You can take a trace here because this is just vect, and this trace is this is the coefficient, and so this is in factorization homology of the sphere. This is an idempotent, so it is an idempotent matrix under the identification with vect, and the trace of this is this number, so it's the dimension of the image.
I might have a better answer.
Okay. But this is the well, this is sort of the trick also from FRS is you put this on a sphere and then you get such a projector and then you get
Easy ways to compute distance, not just for projective.
Sorry?
There are easy ways to compute these dimensions and not just for projective for any objects. But you cannot do it with scale techniques, but you can do it with category theory.
I mean, you might be able to exit. Yeah, okay. Yes. Okay, that might be true. I mean, the non-projective objects will not give you. They will not give you admissible scans.
No, it will not give you, but yeah, I have a categorical procedure.
And you will tell us next week in your talk, right?
Okay, I was still.
Next talk will be related, I think.
Somewhat.
Full center, about full center, but it will be next week. Good. Other questions, comments?
So, I guess you're stuck in this case where you're taking the same right movers and left movers a bit. Is there any, not, of course, not technically, I think that's a bit too much to ask, but do you have any hints about, from their perspective, how to think about taking different right movers and left movers?
So, I mean, I would hope that this would still go through in more or less the same way, but I did not do this so far. I mean, so the thing is that if you,
I can put it into this, is there some?
Yeah, I mean, the reason why, I mean, is if you have different colorings for the different circles, and also if maybe you wanted to, instead of a Rubini algebra, wanted to talk about modular categories, you would need all these stratifications. You would need colored operas. I did not want to do that, but I would not think that this is fundamental.
Okay.
Other questions? Oh, Anna? No.
Yeah.
Okay.
Maybe one comment before you close. There is on the web page, on the Indico web page, there's a poll. which you should fill in if you are leaving the institute or after the end of the conference. So please fill it in. This is for the feedback is important. Yeah, so you're helping the organizers and you're helping the institute. So please don't forget it.
Yeah.
Sorry.
Okay, on this positive note, let's thank. Monday, Tuesday.
Maybe you already decided somewhere.
Con anh như vậy là
special